All right, so we're diving into some pretty fascinating research today. And when I say fascinating, I mean kind of concerning because it's about my health. You've shared some papers on this gene, PIK3CA, and its role in triple negative breast cancer, or TNBC, as the cool kids call it. And this gene seems like a real troublemaker, wouldn't you say?
Yeah, PIK3CA is definitely one of those genes that when it's mutated can really throw a wrench in the works. Basically, it messes with your cell's ability to regulate themselves, which, you know, not ideal, especially when you're talking about a fast-growing cancer like TNBC.
Okay, so back up a sec. For those of us who didn't ace genetics, what exactly is this PIK3CA? Like on a normal day, what's it up to in our cells?
Okay, so imagine your cells are like bustling cities, right? Lots going on. PIK3CA is like a traffic light system, making sure everything runs smoothly. It tells cells when to grow, when to divide, even when to take a break.
But then when this mutation happens, it's like,
Someone took those traffic lights and just stuck them on green permanently. Things pile up, get chaotic cells are growing and dividing with no off switch. That traffic jam, that's basically cancer in a nutshell.
and we're seeing these PIK3CA mutations a lot with TNBC, right? Especially in my case.
Yeah, and that's why we're really focusing on it. We're talking 40% of TNBC cases have these mutations, so it's clearly a major player.
So this isn't just some random glitch, it's central to how this thing behaves.
Absolutely. And to make things even more interesting, TNBC isn't just one disease. There are subtypes, each with its own quirks.
Mhm.
Like how they respond to treatment can be really different.
Adding to the complexity, huh?
Oh, for sure. But two big ones to know are basal-like 1, we call it BL1 for short, and luminal androgen receptor, or LAR. Research shows that LAR is way more likely to have these PIK3CA mutations.
Okay, so different subtypes. PIK3CA is involved in at least one, maybe more. But it's not just about the tumor growing in one place, right? You mentioned this tumor tropism thing earlier.
Ah, you're right. Tumor tropism is all about a tumor's ability to spread, and it's huge. It's almost like these mutations give the cancer cells a map and keys to other parts of the body.
So not only is it growing out of control where it started, but it's also driving where it goes next.
Exactly. And here's the thing. Different cancers seem to have preferences, like a homing beacon. Some go for the bones, others the lungs.
Okay, so for me, where's this unruly PIK3CA potentially sending things? What should I be watching out for?
One thing we see a lot with these mutations is an increased risk of the cancer spreading to the bones. It's not 100% clear why, but it seems like the mutated gene makes it really easy for the cancer cells to settle in the bone tissue and start growing there.
So it's less about PIK3CA sending them there directly and more like it prepped the environment, made it comfy for them, they show up.
Exactly. Like rolling out the red carpet, making it easy for the cancer cells to get comfortable and set up shop.
So how does knowing this about the bones change how we treat things?
It makes us way more vigilant about monitoring for bone mets. And if they do show up, we've got to be ready with therapies that are really good at targeting them specifically. Early detection is key.
Proactive, not reactive. Got it.
Exactly. We've got to use every tool we have.
So we've got this picture of PIK3CA potentially directing traffic, making places like bones more vulnerable. But it's not working alone, is it? There was that crosstalk you mentioned.
You're picking up on all the right things. PIK3CA isn't a solo act here. It's like a whole network of molecular pathways all influencing each other, and it can make the cancer even more aggressive.
Okay, less like a single traffic light, more like the whole system's going haywire at once.
That's a great way to put it. And one of the big players in this network is the Ras-Raf-Mac-Kirk pathway. Think of it as PIK3CA's partner in crime.
A dynamic duo we could definitely do without. So what's so special about this Ras-Raf? What was it again?
Ras-Raf-Mac-Kirk pathway. That's a mouthful, right?
Mhm.
But basically, while PIK3CA is mostly about cell growth and survival, this pathway is about proliferation, differentiation, even migration.
So not just how fast they're multiplying, but what they turn into and where they're going.
You got it. It's like it hands out blueprints and travel brochures, telling those cancer cells what to be and where to go next.
And when those two pathways, PIK3CA and that other one, start chatting, that's when things get really bad, huh?
You said it. This crosstalk amplifies everything, making the tumor way harder to control.
So PIK3CA's directing traffic, now it's on the party line, spreading the word, making things worse. Any other pathways we need to be worried about in this network?
There is one more, super relevant to this whole tumor tropism thing, the epithelial to mesenchymal transition, or EMT.
EMT, that sounds pretty intense.
It is a bit of a mouthful, but it's how cancer cells break away from the main tumor and spread. Think of it like this. They ditch their old identities,
Yeah.
gear up for travel. It's the epithelial to mesenchymal transition, or EMT for short. Like they traded their commuter car for an off-road vehicle ready for anything.
Go on rogue.
Exactly. And guess what? Both PIK3CA and that raised pathway, they're involved in this too. It's like they're handing out the escape plans.
And I'm guessing this whole breaking free, traveling, setting up shop elsewhere, that takes resources. Like you need roads and infrastructure.
Spot on. And that's where angiogenesis comes in, the formation of new blood vessels.
So the cancer cells build their own supply lines.
You got it. And yep, PIK3CA is involved here too. It stimulates the production of VEGF, which is basically the construction foreman for those new blood vessels.
So this tumor's got it all planned out, and PIK3CA is right there in the thick of it. It's a little scary how organized it all seems.
That's why understanding this gene, how it talks to these other pathways, it's crucial. That's how we find the weak points, the targets for treatment.
So it's like a cellular war zone in there, and we need to figure out the best way to fight back. Knowing where to intervene in all that crosstalk seems crucial. How do you even target something like PIK3CA?
That is the million-dollar question. And the good news is, researchers are really making some headway. One of the most promising things on the horizon are drugs designed to target those PIK3CA mutations directly. It's like creating a personalized roadblock for those out-of-control growth signals we were talking about.
So instead of just hitting everything with chemo, it's more like a smart bomb, zeroing in on just the mutated cells.
Exactly, and we've got a few promising drugs already. Alpelisib is one example. It specifically inhibits the activity of that mutated PIK3CA protein.
So it's like putting that stop sign right back up in front of those permanently green traffic lights.
Perfect analogy.
Yeah.
And it's showing real results in clinical trials. We're talking actually shrinking tumors in people with those PIK3CA mutated cancers.
That's amazing. Are there others? Other drugs like that?
There are a few. Caselisib is another one that's looking really good. It's a dual inhibitor, meaning it targets PIK3CA and another protein in that pathway, AKT. Remember we talked about that one earlier.
Right, so it's like setting up two roadblocks instead of one, making it even harder for those signals to get through.
You got it. Hitting that pathway at 2 points, it's potentially even more effective.
That's really encouraging. It's like researchers are finally starting to outsmart these cancer cells, but you did say they're adaptable, right? Like, could they just find a way around these roadblocks eventually?
That's the big question. And unfortunately, yeah, they can. Cancer cells are constantly mutating, evolving to escape whatever we throw at them. That's why drug resistance is such a big challenge.
So it's this constant back and forth, trying to stay one step ahead of them. Is there any way to, like, anticipate that, prevent that resistance from developing?
That's where the whole world of personalized medicine comes in. It's not one size fits all anymore. We want to tailor the treatment plan to your unique tumor, you know?
So not just what kind of cancer, but the specifics of those cancer cells.
Exactly. By looking at the genetic makeup of your tumor, we can identify weak spots, predict which drugs will work best, and even see which resistance mechanisms might pop up.
It's like having the enemy's playbook, knowing what they'll do before they do it. Are there tests for that? Specific analyses that can give you that level of detail?
We have this thing called comprehensive genomic profiling. It's like looking at the entire blueprint of the tumor, not just a snapshot.
Whoa, going from a basic map to, like, the Google Earth view.
Exactly. And with that information, we can be way more strategic.
So in my case, what would that reveal? What could we learn from my tumor's blueprint?
It would show us exactly which PIK3CA mutations you have, how active they are, even what other genetic things might be going on in there. It's about getting the full picture.
And with that, you can predict how I'd respond to these drugs, or maybe even see other options we haven't thought of yet.
Exactly. We're not just treating the cancer. We're trying to outmaneuver it, using its own biology against it.
That's incredible. It sounds like personalized medicine could be revolutionary, not just for TNBC, but for any kind of cancer. But I'm guessing it's not easy. There must be challenges.
You're right. It's still a very new field. One of the biggest hurdles is just the sheer amount of data we get from these genomic profiles. It takes time and expertise to make sense of it all, you know?
So it's not just having the data, it's knowing how to read it, how to translate it into something useful. What other challenges are there? What are researchers wrestling with in this area?
Well, cancer is complicated. Even within the same tumor, you can have different groups of cells, and they might have slightly different genetic profiles.
Oh, wow. So it's like trying to hit a moving target. Some cells might respond differently to the same treatment.
Exactly. It's complex, but we're learning more all the time, which is why this research into how these cells interact, how resistance develops, it's all crucial.
It's a constant race, but it sounds like we're headed in the right direction. It's a lot to take in, but it does sound like we're making progress. So for everyone listening, what's the biggest takeaway you want them to have from all this?
About PIK3CA and its role in TNBC? Honestly, knowledge is power. The more we understand about this gene, the mutations, how it messes with those other pathways, the clearer the picture is of how your cancer works.
Hmm.
And that's how you make the best treatment decisions.
Like instead of wandering in the dark, we've got a map and a flashlight now.
Exactly. And with those tools, we can start getting really specific with treatment. Maybe it's alpelisib or tasilisib blocking those signals,
Hmm.
or something else entirely, based on your tumor's own genetic code.
So less like a one-size-fits-all approach and more like, I don't know, a tailor-made suit. It's got to fit you perfectly.
Precisely. There are always challenges. Medicine's never easy, especially not with cancer. But these new therapies, this personalized approach, it gives me a lot of hope
Oh,
for everyone.
it's good to hear someone's going to be staying ahead of these tricky cancer cells, right?
We're working on it.
Good. Okay, before we wrap up, I always like to leave folks with something to think about. And after this deep dive, here's what's sticking with Emmy. We talked about those PIK3CA mutations making it easy for cancer to spread to the bones, right? But what if we could, I don't know, reverse that?
Interesting thought. What are you thinking?
So instead of just blocking the signals, what if we could reprogram them? Turn those welcoming beacons into, I don't know, dead ends. So instead of attracting cancer to the bones, those signals would actually push it away from vital organs.
That's ambitious, but not impossible. I mean, researchers are finding ways to manipulate these signals already.
Right. And yeah, maybe it's a long shot, but the idea of using the cancer's own tools against it, that's pretty exciting.
It's definitely worth exploring.
It is. And on that note, that's a wrap on PIK3CA and TNBC for today. Thanks for joining us on this deep dive, everyone, and we'll be back soon with more explorations into the world of cancer research.